Right, awesome. Hello, everyone. Welcome back to our online quantum chaos seminars. Thank you for joining us today again. As usual, I'll just remind everyone that you can interact with us and the speaker through the live chat, and we encourage you to send us messages and particularly questions for today's speaker if you want throughout the talk or particularly at the Q&A session at the end. Today, it's our pleasure to introduce our speaker, Shreya Vardhan. Shreya got her Bachelor of Science degree from Harvard University, and she's currently doing her PhD at MIT, working on topics related to dynamics of many-body quantum systems and quantum chaos, and also in relation to topics like in high-energy physics, like ADS-CFT. Today, she's going to be telling us about the universal approximation for entanglement entropies of equilibrated pure states. So we really look forward to your talk, Shreya, and take it away whenever you want.
Okay, great. Thanks a lot. Thank you for the invitation. So today I'm going to be talking about some work with my advisor, Honglu. And mostly I'm going to be focused on this paper from this August. And I'll also talk a little bit about how it connects to some work from previous papers. Okay, so I'm going to start with just some general background and motivations to provide context for the question that we'll be interested in. So quite generally, we expect that in quantum, in non-integrable many-body systems, when we start with some generic initial state, then at late times, it should evolve to some kind of equilibrium state. And we'll be interested in this question in the context of quantum mechanics. So we'll start with some pure state in an isolated quantum many-body system. And as usual, we'll find the time-evolved state just by applying the unitary time evolution of that system on the initial state. So in quantum mechanics, when we say that this state equilibrates, it means that at late times, it macroscopically resembles some kind of equilibrium density matrix, rho equilibrium. So this macroscopic resemblance means that in particular, if we look at expectation values of some few body observables O in the time-evolved state, then these will be close to the values of the same observables in the equilibrium density matrix. Okay. But in quantum mechanics, because of this unitary time evolution, we have certain new kinds of constraints. So in particular, pure states always have to evolve to pure states, which means that this time-evolved pure state cannot actually be equal to this equilibrium density matrix, rho equilibrium, which is a mixed state. And one set of observables which can distinguish between pure and mixed states are the Renyi entropies. So these are found by just selecting some subsystem of the full system and finding the reduced density matrix in that subsystem, and then taking traces of powers of the reduced density matrix. Okay, so the n going to one limit of this expression is the von Neumann entropy, which is familiar to many of us. And so these quantities in any pure state, we have the constraint that the nth Renyi entropy of some subsystem A is equal to that of its complement A bar. And this constraint is not true for a mixed state like equilibrium. So then our main question in this talk will be, what form do the Renyi entropies of this time-evolved macroscopically equilibrated state take at late times? So somehow this has to, like these Renyi entropies know that this state is not actually equal to rho equilibrium, but they have to somehow also capture the effects of equilibration, right? So that's what we're going to try to understand. And so this question is important in any quantum many-body system, but it has historically been considered to be of fundamental importance in the context of black holes. Okay, so let me first just present a very simple abstract version of the process of formation and evaporation of a black hole. So we start with some isolated star, which is in a pure state, psi 0. And then the star can undergo gravitational collapse to form a black hole. And eventually this black hole is often found to radiate. And as a result of this radiation, in many cases, it evaporates. Okay. But these black holes show several macroscopic behaviors which resemble those of thermal states. Okay, so in particular, we can see that they emit thermal radiation at some temperature. and they can be associated with an entropy, and this entropy satisfies standard thermodynamic relations, which involve this temperature. And we can also look at correlation functions of few body observables, and we find that such correlation functions take thermal values. Okay, so in many ways, black holes behave like thermal states, but if we assume that whatever theory governs the formation and radiation of a black hole is a theory of unitary quantum mechanics, then these should be equilibrated pure states as opposed to mixed states. Okay, so this means that these are an example of the types of states we've been considering. And so in particular, if at late times, the full system consists of the black hole, B, and its emitted radiation, R, then because of this constraint on pure states, we must always find that the nth Renyi entropy of the black hole is equal to the nth Renyi entropy of the radiation. Okay, but several decades ago now, an important calculation was done by Hawking of these quantities in semi-classical gravity. And it was found that from this calculation, it seemed that the nth Renyi entropy of the black hole is not equal to that of the radiation. So this was Hawking's famous information loss paradox. And the central question in trying to resolve this paradox is, how can we obtain a unitary result for the entanglement entropies of an evaporating black hole at late times? And for us, this is just going to be a subset of the previous question that we asked about general thermalizing quantum many-body systems. Okay. Cool. So, so some progress towards answering this question was made several years ago by these people. And they did a very simple calculation, which just involved considering any quantum mechanical system, L, which could be subdivided into two parts, A and A bar. And then they considered what happens if you take any pure, if you take all possible pure states in the full system and just average over them with the uniform measure. Okay, so they averaged the entanglement entropies of A and A bar over all pure states with the Haar measure. And this expression has a particularly simple form when one of the subsystems is much smaller than the other. So it can also be written down more generally, but in this limit, we find that the entanglement entropy of A is equal to that of A bar. And it's just given by the minimum of the log of dA and dA bar. Okay, so, so this is something that's manifestly symmetric under A and A bar. And they could also show in these calculations that if the dimension of the full Hilbert space is large, then the standard deviation about this average is small. So that means that if you pick some typical pure state in the combined system, then it would have this value of the entanglement entropies. Okay, so two nice things about this result are firstly, that it's consistent with unitarity manifestly. And also when dA is much smaller than dA bar, then this value is essentially what you would expect from a thermal state at infinite temperature. Okay, so this expression gives us some kind of a hint of what we should expect in general for the value of the entanglement entropy in a state which is both thermalized and consistent with unitarity. But then this raises several questions. So for example, it's not clear how to obtain a generalization of this expression for finite temperature equilibration. And it's also not clear how to generalize this to infinite dimensional Hilbert spaces, because in infinite dimensional Hilbert spaces, we don't really have a similar average to the Haar average. So we don't know, for example, how to do this in quantum field theories. And this Haar average can be thought of as maybe giving some kind of leading order behavior of the entanglement entropies when you have equilibration to infinite temperature. But it would be nice if we could find some kind of systematically improvable approximation so that in principle, we could also find results beyond leading order, we could find fluctuations, etc. Okay, so these are some of the questions that, that we wanted to address in the course of our work. Okay, so the plan for the rest of the talk is that I'm first going to explain how to derive an approximation method for finding entanglement entropies in equilibrated pure states. And this will address some of the problems that I mentioned on the previous slides. So it'll be applicable for finite temperatures and for infinite dimensional Hilbert spaces. And it will also be an approximation which can in principle be systematically improved. And so after developing this approximation method, I'll talk a little bit about its general mathematical structure and physical implications. And then I'll discuss some applications to the black hole information paradox. And hopefully if there's time at the end, I'll talk a little bit about thermalization to infinite temperature from the perspective of operator growth. Okay, so are there any questions at this point? Okay, cool. Great, so the next few slides will just be about developing this approximation method. So our starting point for this approximation is that we assume that we can associate some equilibrium density matrix, rho equilibrium, which our time-evolved state resembles at late times. So we'll assume that there's some thermalization timescale Ts, which precisely what it is not so important for our purposes. But after this time, we'll assume that we can identify some rho equilibrium, which can be associated with this state. Okay, and any such equilibrium density matrix usually has the form of I alpha divided by Z alpha. So this is some effective identity operator for the accessible part of the Hilbert space from our initial state. And the Z alpha is some effective Hilbert space dimension. Okay, and in everything that we do, we'll be assuming that the Z alpha is much greater than 1. So we'll be assuming very large effective dimension. And of course, because I alpha is an equilibrium density matrix, it makes sense that it should always be invariant under the time evolution of the system. Okay, so some yeah.
Can I ask a quick question?
Yeah.
Can you specify what you mean by resembles? That's this equilibrium density matrix needs to resemble that of the evolved state?
Yeah, so when I say it macroscopically resembles, it means that, for example, I gave an example in the first slide where if you look at expectation values of some few body observables, then for generic observables, you should find that the expectation value in rho equilibrium is the same as the expectation value in psi of t.
Okay, thanks.
Yeah, so we'll actually see all of these facts come out of making our approximation. But for now, and I'll explain exactly how we use rho equilibrium in the approximation. But for now, we're just assuming that there's some equilibrium density matrix which we can always identify with the late time psi of t. Okay. Cool. So some examples of how we make this identification is, in one case, we can just take this I alpha to be equal to the identity operator on the full system. So then this Z of alpha is just equal to the actual dimension of the full Hilbert space. And this choice would make sense, for instance, if we had a system without energy conservation so that there were no constraints on the final state that you could go to from the initial state. Or if you had some if you had some initial state in a system with energy conservation, which was somehow, because of the dynamics, all possible states were accessible, then this would be a good choice. But if your initial state is something which has a very narrow range of energies in it, then the microcanonical ensemble is a good choice. So the microcanonical ensemble, I alpha is just formed by selecting some energy E and taking some small interval around that energy and just considering an equal mixture of energy eigenstates with those energy eigenvalues. And then another choice is the canonical ensemble. So here I beta is taken to be e to the minus beta h. And this beta is essentially determined by the expectation value of the energy in the initial state. And this choice would be relevant, for example, if you had some initial state which had a relatively wide distribution of energies, but there would still be some restrictions in the Hilbert space due to energy conservation. Okay, so this choice has to be physically motivated by the form of the initial state. But we're going to assume that you can always make a well-defined choice for this. Okay, so now the actual quantities that we want to approximate are these time-evolved Renyi entropies. And in particular, I'll usually be talking in terms of the exponential of the Renyi entropy. So this quantity e to the minus n minus 1 Sn, which is just the trace of powers of the reduced density matrix. And so the next two slides, I'm just going to provide two kinds of different expressions for this quantity as a transition amplitude in 2n copies of the original Hilbert space. Okay. So the first representation is just a path integral representation of this quantity, which is obtained using whatever path integral representation we have of the time evolution operator. Okay, so in this, there are some boundary conditions, which I haven't written down very carefully, but roughly this path integral lives on 2n contours. And so there are n forward evolutions and n backward evolutions. And the initial state for this path integral is essentially determined by the initial state rho 0. And the final state is determined by the pattern of traces in this expression. Okay. And the actual integrand in this path integral is a phase which involves a sum of n terms of s phi and n terms of minus s phi I prime. Okay. So this is the structure of this expression. And one thing that we can immediately note is that if we just set each forward evolution equal to some backward evolution, so if we set the fields along some forward evolution equal to those on some backward evolution, it doesn't necessarily have to be the same one. Then we find that this phase just becomes 0 in the path integral. Okay. So this means that if we set phi I equal to phi prime of sigma I for any permutation in Sn, then the phase vanishes. So this path integral just becomes some constant in time. Whereas if we have some chaotic system at late times, then we might expect that in all configurations other than these special ones, we should overall find that we have a large number of phases which are growing with time. So roughly, we might expect that they would all cancel with each other, and all we would be left with would be this kind of stationary contribution. Okay, but if we just naively put this condition into this path integral, then we find that we get a divergent answer from doing this. So this is not actually a well-defined thing to do, but it gives some heuristic idea of why these configurations which are associated with permutations should be important at late times. So this is an observation that was made in this paper by Zhou and Nuhu. And so roughly what we're going to try to do in our approximation is find some systematic way of projecting onto such configurations. And this will also end up involving the density matrix rho equilibrium that we discussed. Okay. Great. So in order to systematically develop this, I need to introduce a lot of notation on this side. So firstly, I'll always be referring to permutations in Sn as sigma or tau in general. And two specific cases that I'll be using a lot will be the identity permutation, which I'll call E. So this will just send every element to itself. And then another important permutation will be this eta, which sends n to n minus 1, n minus 1 to n minus 2, and so on, and 1 to n. So I'm using the cycle representation of this. So this permutation has only one cycle. Okay. And then for any operator O acting on one copy of the Hilbert space and any permutation sigma in Sn, I'll define a state which is associated with this operator and this permutation on 2n copies of the Hilbert space. Okay. And the way this is defined is that if I have some basis I for one copy of the Hilbert space, then I can use this basis on 2n copies. And then this overlap with this basis element is given by n factors of expectation values of O, and which states you take the expectation values between is determined by the permutation sigma. Okay. So you can also consider the special case where this operator O is just the identity. And in this case, I'll just get delta functions between various basis states. And in this case, I'll just label it with just the permutation and not write down the identity explicitly. So let me give you a couple of examples of what defining such states does for us. So if we take the overlap of OE for any operator O with just the state labeled by E, then we find that this becomes equal to the trace of O to the power of n. Okay. Whereas if we took the overlap of the same state with the permutation eta, then we would find that we first multiply O by itself n times and then take the trace. Okay, so yeah, so different overlaps will give different kinds of trace patterns like this. And of course, we can also define these O sigma states within a single copy, within a subsystem of the full system, just by using the basis for that subsystem. So then using this notation, we can rewrite our expression for the exponential of the n through any entropy in this form. So again, this looks like a transition amplitude where the initial state is determined by rho 0 and the final state is determined by the pattern of traces. And the time evolution is just given by 2n copies of the original time evolution. Okay, but but in particular, you can see that taking the identity permutation in A bar corresponds to first taking the trace and then multiplying n times, like we do in this expression in A bar. And in A, we first multiply the matrix and then take the trace, so that's why you end up with an eta here. Okay, but anyway, so we've ended up with this kind of expression for this quantity, and we'll be making our further approximations using this expression. Okay. Cool. So essentially, in order to define a regularized version of the projection onto permutation states, we can define a projector onto states spanned by I alpha sigma in 2n copies of the Hilbert space. Okay, so I've just written down this projector to give an explicit expression. It doesn't really matter what the specific factors in this are. So these are introduced essentially just to make the projector square to itself. But once I define such a projector onto this subset of states, then I can always also define an orthogonal projector. So I can decompose the identity on 2n copies of the Hilbert space in terms of P alpha and its orthogonal projector. And then I can just plug this back into my original expression for the time evolved n through any entropy. So that's all I've done at this point. But then from the fact that I alpha is invariant under the action of U, we also find that this projector P alpha is invariant under acting with U times U dagger on the left or acting on the right. Okay, so as a result of that, this sum simplifies into two terms. So one term is independent of time, and this just involves inserting this projector instead of the time evolution in this expression. And then we have some time-dependent term, which involves this projector onto the remaining subspace outside of the permutation subspace. And so the key assumption that we make in our approximation is that we can ignore this second term, which involves projecting in the orthogonal subspace, and we only keep the projector onto the permutations. Okay, so our approximation is to just keep this term and throw out this one. So here I've just written down what our approximation is. And then using the fact that the effective Hilbert space dimension is large, we can further simplify this. So in the end, we just end up with a term corresponding to each element of the permutation group. And it's very simple. It just involves taking this inner product of the final state determined by the traces with I alpha tau. Okay, and in particular, note that the dependence on the specific initial state is dropped out, and this expression ends up depending only on I alpha. Okay. Great. So this is the expression that I'll be discussing for the remainder of the talk. But first, let me try to justify it a little more. So the exact expression was just given by this quantity here. And then note that if we just average over all time evolution operators U with the Haar measure in this expression, then as was noted in this paper, you just find that you get the projector onto the states associated with the identity operator. Okay. So in this case, just averaging over all time evolution operators without any constraint gives us the infinite temperature version of our equilibrium approximation. And we can also consider the variance under this average. We find that it's much smaller than the estimate in the limit of large Hilbert space dimension. Okay, so that means that if we pick some random time evolution operator without requiring any constraints on energy conservation or anything like that, then we find that indeed our equilibrium approximation is very close to the actual answer. Okay, But for other choices, for cases where we do have constraints in the Hilbert space, it isn't really easy to define a similar average over all time evolution operators. So in this case, we need to do something else. So we define essentially a self-consistency criterion, which is analogous to finding this variance. Okay, so in particular, I mentioned what the equilibrium approximation is for the time-evolved Renyi entropies, but you can make a similar approximation for any quantity, which can be written in this form, where you have some 2q copies of the time evolution operator, and you have some initial state that's determined by rho 0. Then you can always replace this with the projector onto the permutations p alpha. So this is how we'll define the equilibrium approximation for some general quantity f. And if f can be written in this form, then the square of f can also be written in the same form. So we can also make an equilibrium approximation for f squared. Okay. And then we can just, yeah.
Before you continue, there's a quick question from the chat.
Yep.
In the previous slide, why did the off-diagonal components disappear? Namely the ones that mix q and p alpha. I think probably in the slide before that.
Here.
Yeah.
Yeah. So that was essentially that came from the fact that p alpha and q are orthogonal to each other.
Okay.
Yeah. So for example, yeah. So it came from a combination of the fact that they're orthogonal and the fact that acting on the left or the right just gives p alpha. So then all of the off-diagonal terms will end up with things involving p alpha times q.
Okay, thanks a lot.
Yep, great. Yeah. So for justifying this approximation, we were discussing the self-consistency criterion. So in order to define this, we just compare the equilibrium approximation for the quantity f squared to the square of the equilibrium approximation for f. And if this approximation is self-consistent, then we should find that this is much smaller than the actual estimate for f squared. Okay. And indeed, we find that for the nth Renyi entropy, this criterion is satisfied whenever the effective Hilbert space dimension is large. Okay. And we can also look at using this general form of the equilibrium approximation. We can also consider other types of quantities. So for example, we can consider this time-evolved operator O of t and its expectation value. So this can be expressed in this form for q equal to 1. Okay. And indeed, we find that its equilibrium approximation is just given by the value of this operator in the equilibrium density matrix. But on physical grounds, we expect that we should be able to make this approximation only when the support of the operator is much smaller than the full system, right? Because in particular, if we could just make this approximation for all possible operators, which were arbitrarily large, then we would just end up finding that the full density matrix is equal to rho equilibrium, which would be wrong. Okay. And indeed, we find that for this quantity, the self-consistency criterion is met only when the support of the operator is much smaller than the full system. Okay. Otherwise, we find that that this deviation is actually comparable to the value of O squared. Okay. But for the Renyi entropies, we find that it's always satisfied when the dimension of the full Hilbert space is large. All right. So then essentially by using similar methods to the ones which were used to calculate the variance, we can also compare the nth power of the equilibrium approximation for the nth power of Zn of A to the nth power of the equilibrium approximation. And we find that these are also very close to each other in the limit of large Hilbert space dimension. So then this lets us verify that if we were actually to find the equilibrium approximation for the nth Renyi entropy, then that can be found by analytic continuation from this expression. And so we find that it does take the value that we would expect, which would involve taking the log of this Zn approximation. Okay. And then by a different kind of analytic continuation, we can show that the von Neumann entropy equilibrium approximation is just given by taking the n going to 1 limit of the nth Renyi entropy. Okay. So we can indirectly find equilibrium approximations for the von Neumann entropy as well. Okay, cool. So now let me just discuss, now that I've developed the approximation and tried to justify it, let me just discuss some general aspects of the mathematical structure. Okay. So recall that the expression that I had was of this form. It involved terms associated with all the different permutations in Sn. And each of these terms can be given a diagrammatic interpretation. So in each of these diagrams, you'll notice that the exterior circle is the same. So that's determined by this final state involving the pattern of traces. And the specific permutations give me different ways of internally connecting these diagrams. Okay, so I've given some examples for some simple permutations in the case of n equal to 6. And here I've used the cycle notation. So this is a permutation with 4 cycles and 1 center 4, 4 center 1, and so on. So one general feature of these diagrams is that the number of solid, so you notice that each diagram has some number of solid loops and some number of dashed loops. And the number of solid loops is just equal to the number of cycles in the permutation tau. And the number of dashed loops is equal to the number of cycles in the permutation eta tau inverse. And we can also roughly estimate the size of each term in terms of the effective Hilbert space dimensions of A and A bar. So we find that the number of powers of dA which appear is equal to the number of dash loops. So it's just equal to this number of cycles in eta inverse tau. And the number of powers of dA bar which appear is equal to the number of cycles in tau. Okay. So then a general fact about permutations in Sn is that the sum of the number of cycles in these two permutations is always less than or equal to n plus 1. But this value of the sum is saturated for a special type of permutations, which are called non-crossing permutations. And these are precisely the ones which in our diagrammatic representation are associated with planar diagrams. Okay, so diagrams like this will saturate this this maximum number of loops, whereas diagrams like this will not. Okay, and in a certain limit, we will find that these contributions are the most relevant, the ones that come from planar diagrams. Okay, and then there is yet another representation of this expression, which is useful, which is a path integral representation. So here I've just written very explicitly what this term looks like in terms of I alpha. So each of these terms associated with tau will involve n factors of matrix elements of I alpha. Okay, and in many cases we know that I alpha can be given some Euclidean path integral representation. For example, in the canonical ensemble, we know that it has a Euclidean path integral representation. And so these n factors will give n path integrals, which go between some initial and final states. And the actual values of these matrix elements will tell us that each final state should be identified with some initial state in this. Okay, so that's what all these delta functions are telling us. And the way in which you identify initial states with final states is done differently in A and A bar. And it's also done differently depending on what the permutation tau is. Okay, so for this example of tau equal to the identity, we just identify these initial and final states cyclically in the region A. And in the region A bar, we identify each initial state with the corresponding final state. But then you get all possible other ways of identifying this depending on what the permutation tau is. Okay, so you get many different patterns in this way. And the upshot of this is that we started, so remember from a few slides ago, we started with an expression which involved a Lorentzian path integral on two n copies of the system. And somehow from our series of approximations, we've ended up with a sum of as many Euclidean path integrals as there are elements in the permutation groups. And each of these Euclidean path integrals is defined on n copies of the system. Okay. So this is a nice way of representing what our final result is. Cool. So now let me talk about some general physical consequences of this structure. So one thing that we can immediately note is that because of properties of these inner products on 2n copies of the Hilbert space, you can show that this expression can be written in a way that's manifestly symmetric under interchanging A and A bar. Okay, so we can directly see that this final approximate expression that we've obtained satisfies the property that the nth Renyi entropy of A is equal to that of A bar. So it satisfies the constraint from unitarity. And the other thing that we can consider is what the dominant contributions are in various regimes. So recall that this was the overall scaling behavior of this expression in terms of the effective dimensions of A and A bar. So we can first consider the limit where the subsystem A is much smaller than A bar. Okay, so in this case, we want to get the largest possible power of dA bar in this expression. And so this is just given by the case where tau is equal to the identity. Okay, so here you get n powers of dA bar and just 1 power of A in this expression. And if you analyze it further, then you see that this is just equal to the nth Renyi entropy of the equilibrium density matrix in the region A. Okay. You can also consider the opposite limit where dA bar is much smaller than dA. And in this case, by a similar analysis, the tau equal to eta term dominates. And we find that the entanglement entropy of this equilibrated pure state in the region A is equal to the nth Renyi entropy of the equilibrium density matrix in the region A bar as opposed to A. Okay. So then if you put these two things together, then you find that you get the expected generalization of Page's result, which is just that the nth Renyi entropy in A is the minimum of the nth Renyi entropies of the equilibrium density matrix in A and A bar. Okay, and because this is the same for all n, we can just analytically continue it to find in this limit what the von Neumann entropy should be of this equilibrated state. Okay, so this is something that is physically expected, and it's nice to be able to recover it. When we consider the limit where both dA and dA bar are large and they're comparable to each other, so their ratio is finite, then in that limit, we want to consider the maximum value of the sum of both of these powers. Okay, so that, you remember, was just given by the permutations which corresponded to planar diagrams, or the non-crossing permutations. So in that case, we just consider the subset of tau, which involves planar diagrams. Okay. Okay, so just to see one example of what this structure does for us in the case where dA and dA bar are comparable to each other. You can just take the infinite temperature case. So you can take I alpha to be equal to 1. And in this case, you get a simple expression which involves all possible powers of dA and dA bar, which sum to n plus 1. And the coefficient of the term where you have dA to the power of k is just given by the number of non-crossing partitions of n objects with k blocks. And that's essentially because of that diagrammatic structure that I described to you before. And then you can also analytically continue this in the n going to 1 limit. And from that, you find that you just get the von Neumann entropy, which was found by Page from this Haar average over all states. But one nice thing about deriving this from the equilibrium approximation is that now we know what part of this expression we've left out for any specific time evolution, right? So we know that this came from like the ZP contribution, and we know that there was this ZQ contribution. So in principle, we can systematically develop corrections to Page's result for a specific time evolution using our approach. Okay, so this was just the simplest case. And then you can also consider the canonical and microcanonical ensembles. So one nice thing is that now using our approach, you can find universal results for pure states that equilibrate to these ensembles, which would be applicable to any quantum many-body system. Okay. And then some features of this result are that both the microcanonical and canonical ensembles will give the same result in the case where dA is much smaller than dA bar. So you just have to appropriately identify beta with the energy with the energy density. But in the case where dA and dA bar are comparable to each other, we find that we get different results for states that equilibrate to these two different ensembles. We can also check how our results compare to previous results. So there was previously an average which was done over a special subset of states called ergodic bipartition states in this paper. And we can check that our result agrees with the result from this average in the microcanonical ensemble case. And there was a different type of average which was done over a special set of states called canonical thermal pure states in this paper. And we can check that our canonical ensemble result agrees with this. But the nice thing here is that these that unlike Page's calculation, these other kinds of averages couldn't really be seen as averages over time evolution operators. So it's nice to be able to obtain these results, these same kinds of results as approximations to the time evolved expression. And it's also nice to be able to see how they emerge from this common structure involving the permutation group. Okay. Great. So far we've considered cases where the full system is compact, so there's some finite time scale after which it thermalizes. But this is not really true, for example, if we have some uncompact system which has local interactions. But here we can modify our prescription. So in this local setup, there would be some subregions of finite size which would thermalize locally at finite times. And so we can define a modification of our equilibrium approximation. So let's just consider the simplest possible example of this, where we have some infinite 1+1 dimensional system, and it has some sharp light cone, say with some light cone velocity equal to 1. So this means that if we're considering some region A at time t, then the only parts of the system which could have influenced it are in this region J of A, which is just obtained by drawing light cones from this initial region. Okay. So then roughly the intuition is that to find the nth Renyi entropy of the region A, the evolution outside of this region J of A should be irrelevant. And this can be made very precise. For example, this argument can be made very precise if you have some circuit structure in your system so that you have a sharp light cone. But if you assume this, then we can further assume that in a highly chaotic system, we just have local equilibration in the full region J of A at time t. So what this means is that we can treat this J of A as our full system, and then just apply the equilibrium approximation to this full system. Okay, so this makes sense if our initial state is a product state as well, so that we don't have to consider entanglement with other possible regions. So if we just apply the equilibrium approximation, then we see that indeed for the nth Renyi entropy of A at time t, we get the minimum of, we get some equilibrium entropy density multiplied by the minimum of the size of A in 2t. So this means that we're getting a behavior where the entanglement entropy initially grows linearly and then saturates at some equilibrium value. Okay, so this is this kind of linear growth followed by saturation is expected in highly chaotic systems quite generally. And in particular, we find that from this expression, we can see that the entanglement velocity VE is equal to 1. And we know that essentially, we know from general arguments that VE always has to be less than or equal to VP, whereas VB always has to be less than or equal to 1, where VB is the velocity that's associated with operator growth. So this means that essentially we're able to make this approximation of just replacing, of just assuming maximally efficient local equilibration in the region J of A, only in cases where this butterfly velocity is saturated and you have maximally fast operator growth. Okay, so this was a kind of side note which might make sense if you've seen previous discussions of operator growth involving the butterfly velocity. But if that didn't make sense, that's fine. Okay, but essentially the upshot of this was that we can define a local version of this approximation, and of course it would be nice to be able to refine it further to be able to see behaviors other than this maximally fast equilibration. Okay. Great. So those were some general applications which would apply to any quantum many-body system. And in the remaining time, I want to talk a little bit about applications to the black hole information paradox. So as I mentioned to you in some of the introductory slides, the key to resolving Hawking's information paradox and showing that black holes don't destroy information is to show that the nth Renyi entropy of the black hole is equal to the nth Renyi entropy of the radiation at all times. Okay, and Hawking's information loss paradox was essentially the fact that his semi-classical calculations seem to predict that the nth Renyi entropy of the radiation becomes much larger than that of the black hole at late times. So roughly, he showed, or his calculations seem to show that the entropy of the radiation just keeps increasing linearly, whereas the entropy of the black hole is decreasing. So at these late times, the radiation has a much larger entropy than the black hole. Okay. And while it was expected that the actual theory of quantum gravity should be a unitary theory, for many decades, it was thought that maybe Hawking's paradox can only be resolved by involving non-perturbative effects from quantum gravity somehow, and that it couldn't be done semi-classically. But in the past year or so, there's been a lot of progress on this question. And one remarkable thing has been that in all of these works, it was showed that you can have a new kind of prescription with some new ingredients, which still involves semi-classical gravity, and which can give a unitary result for these entanglement entropies. Okay. And so from a path integral perspective, this calculation is as follows. So this is going to be a very cartoonish representation of their calculation, just to capture the essential features. But to calculate the second Renyi entropy of the radiation, for instance, they considered a case where you had two replicas of the system. And they found that Hawking's result comes from considering a gravitational path integral in a topology where these two replicas are disconnected from each other. Okay, so essentially the path integral involves just integrating over all possible metrics with this disconnected topology. Okay, and it was found that this result leads to Hawking's usual prediction of information loss, where the entanglement entropy of the radiation becomes much larger than that of the black hole at late times. But it was found that if you include another type of topology in the calculation, where these two the black holes in these two replicas are connected to each other, then you actually are able to recover this unitary result where the entanglement entropy of the black hole is equal to that of the radiation. Okay, so such kinds of geometries where where the gravitational path integral actually connects different replicas were known as replica wormholes. And that was done in all of these papers. Okay, so this was a nice result that that replica wormholes could give a unitary result, but this was a bit of an ad hoc prescription, and it wasn't really understood what the fundamental reason is for including these replica wormholes and why they always seem to give a unitary result. Okay. So where our work comes in is that we showed that essentially by applying the equilibrium approximation to these kinds of setups, like the ones that were considered in these papers, you can actually derive these replica wormholes, and you can derive precisely their prescription for calculating the nth Renyi entropy. And the crux of this was that these unconventional geometries, so remember a few slides ago, I introduced these Euclidean path integrals, which had different types of boundary conditions, depending on the permutation tau. And essentially those unconventional geometries, which came from terms other than tau equal to the identity, correspond to these geometries where you have replica wormholes in the gravity description. Okay. And now that we understand how to obtain the prescription for replica wormholes from our equilibrium approximation, this is nice because this can in principle also be applied to other kinds of black hole models, where it can give precise prescriptions for when and how replica wormholes should be included. And of course, now we understand there was a very general reason why our approximation gives a unitary result, which is manifestly symmetric under A and A bar. So this also explains why replica wormholes always seem to give a unitary result. Okay. Cool. Were there any questions at this point? Okay. Yeah, so another thing that we're able to do by applying our equilibrium approximation to this problem is to clarify a question related to whether semi-classical gravity computes averages. Okay, so in this paper, it was noted that including replica wormholes leads to certain kinds of results which resemble ensemble averages rather than exact quantities. For example, it seemed that if you just applied their prescription to calculating the square of this matrix element of the reduced density matrix for the radiation, then it seemed that this quantity is not equal to what you get by actually multiplying the values of these overlaps obtained by their prescription. Okay, so so the fact that this expression doesn't factorize can make sense, for example, if each of these quantities which is being calculated is actually an average rather than an exact quantity. And so this suggested the question of whether somehow semi-classical gravity is intrinsically calculating an ensemble average. But essentially, we showed that these expressions should be thought of as approximate expressions, but they can be thought of as approximate expressions within a single theory, as opposed to an average over various Hamiltonians, because essentially this was the late time approximation for a single Hamiltonian in our case. So an ensemble of theories is not needed for doing this. And moreover, there isn't anything about this non-factorization that seems to come directly from using semi-classical gravity, because essentially we found we're able to estimate the values of these terms from our equilibrium approximation even before we apply the semi-classical prescription to the actual calculation of these quantities, which means that somehow the non-factorization is coming from the Euclidean path integrals even before we use semi-classical gravity to compute the Euclidean path integral. So semi-classical gravity itself doesn't really have to do anything with, semi-classical gravity doesn't have to be the reason for the ensemble average. Okay. Great. So that was all I wanted to say about the applications to gravity. And yeah, it seems I have about 5 minutes left. So I'm going to try to use the remaining time to talk about these results from a slightly different perspective involving operator growth. And this will be mostly in the infinite temperature case. Okay. So in general, we expect that the kinds of systems which equilibrate are usually chaotic systems. And in such systems, we've, from a lot of recent work started by these authors and continued by many others, we have a sort of general picture of how the Heisenberg evolution of operators behaves in chaotic systems. So if we consider an operator which initially has support in some small subsystem of the chaotic system, then we expect that the support of this operator should, in general, grow with time. So for instance, if we have some spin chain system, then we expect that if we start with an operator which is localized on one site, then as it evolves in time, its support should grow, say, along some light cone if you have local interactions. Okay. But one thing that we pointed out in this paper from last year was that within the growing support of the operator, it's important to consider the small probability that it becomes equal to the identity in any subregion. Okay, so to be concrete, if we start with some operator in a local system, which is growing along some light cone, then at late times, its time evolution can be decomposed into two parts. One part is equal to the identity in A bar, and the other part is orthogonal to the identity. Sorry, one part is equal to the identity in the region A, and the other part is orthogonal to the identity in the region A. And if this part O1 of T, which is trivial in the region A, exists, then we refer to this as void formation from the operator O in the region A. Okay. And because of the picture of operator growth that I mentioned in the beginning, we expect that this probability should be small at late times in chaotic systems. But we find that actually considering this probability in the form that it takes has several important consequences. So the one that's most important for what I'll be talking about today is that it's important for ensuring the unitarity of entanglement growth in any system. But we can also show, as we discussed in our paper, that such processes are important for generating multipartite entanglement between disjoint regions. And they're also important for explaining differences in entanglement growth between integrable and chaotic systems in many cases. Okay. But today I'll mostly be focusing on this first application in a very simple setup. So just consider some compact system, which we expect will equilibrate to infinite temperature. Okay, so in this, we can always write the initial density matrix as a sum of two parts, just from the fact that it's normalized. We can write it as the sum of a part which is traceless, which is this rho hat, and the identity divided by the dimension of the Hilbert space. Okay, so now if we assume that the probability of void formation in any subregion from this rho hat is just 0, then we would find that this part of the operator doesn't really evolve. And the only part which contributes when we take a trace in the region A bar comes from this. Okay, so we would essentially find, if we made this assumption, that the entanglement entropy of the region A is just given by the log of the dimension of A. And this is something that's manifestly not symmetric between interchanging A and A bar. So it doesn't agree with this expression that we would obtain from the equilibrium approximation, which would be that we would take the minimum of the log of dA and dA bar. Okay, so essentially what this means is that to include the contributions from the tau not equal to identity terms in our equilibrium approximation, which gave us a unitary result for this quantity, from an operator growth perspective, what we need to consider is these probabilities of void formation in the region A bar. Okay. And then we can, if we assume that we have equilibration to infinite temperatures, that we have this form of the nth Renyi entropy at late times, then from this we can deduce what form we need for the weight of the part of the time evolved density matrix, which has a void in the region A bar. Okay, so if we just take the trace of this rho 1 part, which has a void in A bar, multiplied by, raised to the power of n, and divided by some version of the norm of the full density matrix, then we find that it has to take this simple form, which depends only on the dimension of the region A bar. Okay, and in fact, we find from a calculation in chaotic local random unitary circuits that this probability takes this simple form for any traceless operator O. Okay, so in such systems, we can see this kind of thermalization to infinite temperatures that's consistent with unitarity as a general consequence of this property of operator growth. And we call this property the random void distribution, and we expect that it should be true in many highly chaotic systems. Okay, so this was just a brief discussion of how to understand some simple aspects of thermalization in terms of operator growth. Cool, so I'll just end with some simple some future directions that we would like to go in. So one thing that we would like to do is try to apply this method to other kinds of observables to get predictions for their equilibrated values. For example, we could try to apply it to the entanglement negativity. And it would also be nice to systematically understand the corrections to the approximation and to get some better estimate of the time scale on which it becomes valid. And it would also be nice to understand whether we can relate this kind of equilibration to a universal property of operator growth in the finite temperature case. So extend what I did in the last few slides to a finite temperature analysis. Great, I think that's all I wanted to say.
Okay, thanks a lot, Shreya, for this great talk. I really enjoyed it. So now if anyone has questions, please feel free to ask them through the chat and we'll put them to Shreya. So I think I'll kick it off. I have a few questions. First, questions kind of orthogonal to what you've been talking about. Mm-hmm. So you have this entanglement in the equilibrated state, but in the beginning you neglected this time-dependent state, this mm-hmm. time-dependent contribution. Can you use this to say something about short-time entanglement growth?
Yeah, so that was kind of what I was talking about very briefly in this slide. Mm-hmm. So here, yeah, so we yeah, so maybe I should talk about this in a little more detail. So when I say you treat this J of A as a full system and apply the equilibrium approximation, this essentially means that I'm applying this simplest version where I'll just say that the nth Renyi entropy of A is the minimum of the entropies in the region A and A bar. So then here, if you treat J of A as the full system, then the region A just has size A, and the region A of bar just has size 2t. So that's essentially where this comes from. So this is able to capture some kind of non-trivial time dependence. But it doesn't, but in principle, this kind of time dependence is not necessarily true in all kinds of systems. For instance, it's expected in many systems that the nth Renyi entropy might have some diffusive behavior or like some t to the 1/2 growth instead of a linear growth. So it would be nice to be able to capture effects like that, which you can't in this most crude form of just applying it in the full light cone. But this was supposed to be like a sort of start towards capturing.
Okay. Yeah. That also kind of leads me to my next question. So what happens if you need to take into account local conservation laws? So okay, they're of course going to show up in your eventual equilibrium row, but will they play a role anywhere else?
Right, so energy conservation, for instance, comes in if you're using this microcanonical ensemble to approximate your final state. We haven't thought a lot about what happens if you have other conserved quantities, apart from the fact that it would change what form your equilibrium density matrix has. Yeah, so in principle, yeah, it's not clear if yeah, if this picture should be modified so that instead of this light cone, you have some different dependence on time for like the part of the initial state which influences this region, or if you need to consider some more contributions from the ZQ part. But I guess we don't really understand the details of the time evolution, even in the case without conservation laws. Yeah, so it's not exactly clear to me how to modify this picture in a case where you have conservation laws.
Okay, thanks. I was just curious. So there don't seem to be any more questions from the chat. So I think we can leave it at that. So thanks again to Shreya for this really interesting seminar. Thanks again to everyone for watching. And next week, we'll be back with a seminar from Vedika Kamani from Stanford. And we should note that the talk is going to happen 2 hours later than our usual time because of time zone differences. So see you all next week. And if you want to get updates, oh, no, there's a question. So would the partition function approach help to explain why there's a crossover at the page time?
Yeah, actually, so yeah, so for the simplest, yeah, so if you were to just, so if you consider the simplest version of the page curve where you just take I alpha to be equal to 1, so you're considering the infinite temperature case, then you get a sharp transition if you only include either these terms which happen in the, so if you only consider the limit where dA is much smaller than dA bar or dA bar is much smaller than dA, then essentially you get the result where you get the minimum of the log of dA and dA bar. So that just looks like a very sharp transition where it's increasing up to the page time, and then you get a decrease in the entanglement entropy after the page time. Whereas if you want to get the crossover, then you essentially, then you would be considering the limit where both dA and dA bar are large, but also comparable to each other. So then that would be like at intermediate times where the black hole and the radiation both have comparable sizes. And then you can get the intermediate terms in the crossover in the infinite temperature case just by including all of these other terms. And in the finite temperature case, more generally, you would take some other choice of I alpha. And then you would consider whatever contributions you get from these other planar diagrams. Yeah, which would be sort of analogous to all of those other terms. But yes, you can get the crossover behavior by considering such terms.
Okay, thanks a lot. That was a good question. So thanks again for also answering this additional question, and we'll be back next week. So see you all then. And if you want to get updates about upcoming talks, feel free to subscribe to our mailing list in the description of this video or subscribe to this YouTube channel.